Hello, everybody. This is going to be on page 14, a worksheet, Continuity Practice with Desmos, Part 2. So our objective today is to state the interval on where the function is continuous. And sometimes when we're trying to state continuity, what we actually want to look at is things that aren't continuous. So there's in math things that we've seen before. Excuse me, I'm yawning. Is proof by contradiction. When you're trying to prove something that is true, look at all the other places where you are not able to prove that it's true, and compile all those, and then you can actually see where your thing is true. That's called reductio ad absurdum. Better hint that we have for you on determining if a function is continuous is now just assume that the function is continuous anywhere on the number line. And if you can find any point of discontinuity on the interval, then take those points out, and the remainder is where the function is continuous. And an even better hint is just thinking of any x value, which x value cannot go into the function. So that's a third way of actually thinking about how we can do this. We have state the intervals in which the function is continuous. We have 6 problems here, and I'll start leading you with all of them. Number 1 is f of x equals sine x. Now, I believe Ms. Schwartz and I's expectations for you guys is to actually know what these graphs look like without Desmos or the vast majority of these graphs, so that by sometime April, these should be very, very fluid for you. Oh man, I'm tired. What time is it? It is 4:44. Is that the morning or is that the afternoon? That is the afternoon. Why am I so tired right now? I don't know, but let's keep going. So let's go ahead and go to the page that I wanted to, which is sine of x. So this is what the graph of sine of x looks like. I can easily go over this graph without lifting my pencil, my writing utensil. This function is continuous everywhere. Now Desmos doesn't do a good job of showing any holes in the graph. So one thing that we can think of though is that is there any x value that I cannot plug into sine? No, I can take the sine of any angle. So the function here, the answer to our question is going to be negative infinity to infinity. That's one option of writing it. Sorry that my handwriting is not as good as Ms. Schwartz's. It never will be. That's fine. A second option that I could go with is all real numbers. This is an interval. Well, it says state intervals. Actually, I'm going to cross this off. Just go with the first one. Negative infinity to infinity is the interval on which the function is continuous. Take any x value. I'll just write that here. Any x value. For any x value, the function is continuous. F of x is continuous. That's what that means here. Okay. Number 2. G of x. So g of x here is equal to the square root of x plus 3. If you remember what a root function looks like, excellent. If you don't remember what that looks like, I'm going to show you. And again, our reminder here is that we do want you to start knowing these on without a calculator. So here's the square root of x plus 3. We'll notice that any number to the left of negative 3, the function does not exist. Even if I zoom out over and over and over and over again, that's all we have. So on the left of negative 3, nothing exists, but on the right of negative 3 and including negative 3, we actually do have a function here. So we can say that the function is continuous for, let's see, so we can say that the function is continuous for x is greater than or equal to negative 3. That would be one way you could write the interval. A second way you could write the interval is negative 3 to infinity. And again, these are all the x values where the function is continuous. All x values where the function is continuous. Now, the hint that I gave you has not come into play just yet, so let's go to number 3. Ooh, the square root of 4 minus x squared for h of x. I'm going to add a new page here because I want you guys to see something here. The square root of 4 minus x squared is a semicircle. And I did this in just one of my classes the other day. And I want to make sure that you're clear as to why that is, because this problem comes up over and over and over and over and over and over again. We have x squared plus y squared equals r squared. This is the equation for a semicircle. Equation, I'm sorry, of a circle, not a semicircle, of a circle. And if I move things over in such a manner, and I try to solve for y, then what I end up getting is something that looks like what we have. A positive side and a negative side. Okay, there we go. This one on the top is going to be a semicircle on the top. This is the top semicircle. I'm just going to do SC for semicircle, not South Carolina. And this one on the bottom is the bottom half of the semicircle. On ours, we have a positive value, which is the square root of 4 minus x squared. So when I graph this, I should expect a radius of 2 centered at 0, 0. So I'm going to go back here. And again, the point of this, that exercise was to make sure that you are very familiar with this type of equation because it will come up over and over and over again in this class. And I just don't know how much experience you've had with that outside of this class. All right, now when I zoom in here, it looks like I get the graph is green. I get x value. I can plug in any x value in between -2 and 2 inclusively. I cannot plug in any number outside of -2 and 2. So to go here, I'm going to say that the function is continuous on -2 to 2, including -2 and 2. So this is option 1. You don't have to do both options, by the way. You could just do 1. Option 2, you could do -2 is less than or equal to x is less than or equal to 2. This is just another way of saying that x is in between -2 and 2 inclusively. And again, each of these is saying that for every x value in that range, in that domain rather, there will be a y value for the function where the function is continuous. Okay, let's go to number 4. Number 4, oh, okay, here we go. We are talking now. Now, number 4 looks like we have a little bit of a lots of math. And when we have a lot of math for this j of x function, what we should look for are things that cannot be plugged into the given function. And I notice that both of these are quadratic, so I'm going to factor these before I graph them. And it looks like they factor into x minus 2 and x minus 1. This also looks like on the bottom it's x minus 3x minus 2. Nope. X plus 6x minus 1. Yes. Okay. I see that there's a factor on the top and the bottom. Okay, that's great. That means that this makes a hole in the graph. This makes a hole at x equals 1. Okay, so that means that where is the function, what x value can not be evaluated? And we're going to pause here because my wife is calling me. And now what we're going to get, so we have a hole at x equals 1, which means that we cannot evaluate 1 into the given function. The second thing is I'm looking at this part right here, and this part is a huge culprit because x plus 6 cannot equal 0, or else we have 0 in the denominator, which means that x cannot equal -6 then when I subtract 6 on both sides. So now we have a vertical asymptote at x equals -6. At x equals -6, and we have a hole at x equals 1. So the intervals of continuity are anywhere that are not those values. So that means that we are going to have a continuity from -infinity to -6, and we'll go and unite that with -6 to 1, and we can also unite that with 1 to infinity. Okay, a different way of writing that would be, why is it doing that? Ding, 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 whoa, okay. Okay, now the other way of writing that could be, actually, I'll leave it like that. That's how I want your answer. Let's go to number 5. Oh, and let's just check our answer with Desmos, since that's what we are doing. We have x squared. I love my Desmos. Over x squared minus 5x plus 6. Okay, so we have, let's see, we got x is equal to, looks like x cannot be equal to 3. Hopefully I entered this equation correctly. Oh, nope, did not enter the equation correctly. That is, I wasted your time. I am so sorry. Let us try that again. Okay, we have a -6. It looks like it's a vertical asymptote. And if I go to x equals 1, let's see here, x equals 1, doing, 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 doing. Oop, and there it is. X equals 1 is undefined. Okay, so let's go on to the next one. And I think you guys saw it instantly there for a second. 2 more to go. X squared and 1 plus x squared. Ooh, interesting. So a lot of students will do, not a lot of students, I've I don't know exactly how you would tackle this one. You are looking for any x value that cannot be evaluated into the given function. So let's try something here. What if I said x squared plus 1 equals 0? Well, then I have x squared equals -1. Then I have x, when I take the square root of both sides, gets the square root of -1, which is I. But I is not on the plane. So what does all of this math mean? Well, what I was trying to do, I tried to see if there was a vertical asymptote. When I tried it, I got something out that was not real. So because I did not get anything out, that means there is no vertical asymptote. If there was a vertical asymptote, I would have gotten a number out. But because I did not get a number out, there was no vertical asymptote. And for a rational function, for a function that has something on the top and something on the bottom, that's the only possible outcome for discontinuities, unless something cancels. Now, some astute students might say, oh, well, we have this x squared and this x squared here. And I'm going to caution to those astute students, do not cancel those out. It's a great, great observation, but the only way we could cancel them out the only way we could cancel terms is if we had the same terms on the top and the bottom. So if the factors were the same. And we do not have the same factors here. The only factors we have are x squared and 1 plus x squared. And this is all a very long way of saying that this function is continuous from -infinity to infinity. I will show this to you on the graph. So let's go and get rid of this guy. I'm just going to do x squared divided by 1 plus x squared. Oop, and it is continuous. And if you don't believe me, we could look at a table too. And it looks like it's continuous everywhere, although that is a horrible way to show it. But this function is continuous everywhere. Let's go to número 6. M of x is equal to tan x. And I just need to check something here. Yeah, I'm good. M of x is equal to tan x. Now, if I plug in a number to tan, I get a number out. But can I plug in any number into tan? Now, for those of us whose unit circle is just not exactly where we want them to, let's just take a look at the graph to see what's going on here. Tan of x. Ah! Okay, so there's a lot of discontinuities here. Muchos. A lot and a lot and a lot of vertical asymptotes here. I would say, I dare say, an infinite amount. So how do we write this then to show where the function is continuous? Well, again, if we want to state where the function is continuous, let's find all the values where x is discontinuous, and then our continuities around those values. So m of x is equal to tan x. Here's a unit circle, and I'm going to give you a little tip for the unit circle when it comes to tan. Tangent is always the slope. Tangent is always the y's over the x's. It's sine over cosine. That's true for those people that remember that. But it's also the y's over the x's. So basically, if I take a y and divide it by x, in order to get something out that I don't want, then that means that I need to have a y over 0, because a y over 0 is undefined. And I'm looking for things that cannot be evaluated into the function. So if I want a y over 0, then I need that x at the bottom to be 0. Well, when x is 0, is right here, that means I have pi over 2 is one of those values. And if you try that on your own and do the tangent of pi over 2, you'll see that tangent of pi over 2 breaks math, undefined. If you do the tangent of 3 pi over 2 as well, let's do purple. 3 pi over 2, that is going to be another value where tangent is undefined. But now we have to support this for multiple rotations around the circle. So in other words, 1 pi over 2 is undefined, 3 pi over 2 is undefined, 5 pi over 2 is undefined, 7 pi over 2 is undefined, 9 pi over 2 is undefined, and negative pi over 2 is undefined, negative 3 pi over 2 is undefined, negative 5 pi over 2 is undefined, So how do I work around this to fit in my 15 minutes here? Well, I work around this by saying 2k plus 1 pi over 2. 2k plus 1 pi over 2 is a very, very, very mathy way of saying odd numbers. You could also say odd values of pi over 2. So for odd, positive, and negative values of pi over 2, the function is discontinuous. So that means that our answer is going to be the intervals on which the function is continuous, all x values except for odd values of positive and negative pi over 2. Thanks for watching, guys.